Hello class, so we're going to go ahead and begin in 9.3, testing the difference between the means and dependent samples. So here we kind of do the same thing as we did in the last section, except we do it with dependent rather than independent samples. And so you'll see some formulas there that we'll refer to on the first slide, but I'll come back to those as we need them. Let's jump into the example here. So dependent meaning kind of like what this question's saying. In other words, what a bank has in their deposits today is dependent upon what it had 3 years ago. So that's how this question would be a dependent. You'll get a lot of these before and after types of studies. So maybe like the chocolate milk study, how did they perform before chocolate milk? How did they perform after chocolate milk, possibly? So let's go ahead and jump into 9.6. A sample of 9 local banks shows their deposits in billions of dollars 3 years ago, and their deposits in billions of dollars today. At alpha equal to 0.05, can it be concluded that the average in deposits for the banks is greater today than it was 3 years ago? Use alpha equal to 0.05. So they give you the list of the 9 different banks, and they give you their deposits 3 years ago and the deposits today. So our job is, we're going to go ahead and conduct a hypothesis test of the mean differences of the bank's deposits 3 years ago and today. So we will start with and state our hypotheses, and that's our step 1, and which will be the null, is that there is no mean difference. So you'll notice a slightly new terminology or symbol here, but that means the mean difference between the two means. So our null is that there is no difference between the two means. Okay, that's how we're going to write that. Our alternative, well, depending on the question, is that we might want to define 3 years ago as our first mean and then today as our second mean, but it says that the bank is greater today than it was 3 years ago, so that the mean difference is greater than 0. Greater than 0. Okay, so this would be our alternative hypothesis. And then we want to define where mu sub d is the mean difference in deposits for banks today versus 3 years ago. Okay, so today minus 3 years ago. So those are the differences that we were calculating. However, actually I might switch that up because the question is actually reversing that. So, well, the way it's outlined is kind of the other way around. Whereas 3 years ago was x1 and today is x2. So meaning is the mean difference. Yeah, let me switch it up. So where mu sub d is the mean difference in deposits for banks 3 years ago. I'm going to switch that up. 3 years ago versus today. Okay, so that actually means 3 years ago minus today's. Okay, that's the differences we're going to. So following up on that, if we go back to the statement at alpha equal to 0.05, can it be concluded that the average in deposits for the bank is greater today than it was 3 years ago? So the way we defined it, 3 years minus today, that would have to mean the mean difference would have to be negative, because if 3 years ago was less than what it was today, let's say like on the first, if you look at the first column, it says 11.42 minus 16.69. Well, that's going to be a negative number. So that's what we're trying to show, that in fact it is greater today than it was 3 years ago. So you'd have to define it as the alternative hypothesis is mu sub d. Now, you could have defined this differently. I'm going to kind of go with it. I could have said the mean difference is greater than 0, like I said, and then defined it the way I defined it earlier. But I'm going to kind of run with how it's done here, because I think it's a little bit, different. But it makes sense. It's just a little bit tougher to think about it, but it does make sense. So I'm going to move on from that. Let's go ahead and go into. So we have the null hypothesis. We're going to go ahead and do step 2, which we want to find the critical value, which doesn't change, right? This is the same thing as it was for every other section. So this is a left-tailed test, and if it's a left-tailed test at alpha equal to 0.05, I'm going to go ahead and do inverse t, because I'm dealing with the samples. So inverse t of area 0.05 and degrees of freedom. The smaller of the two sample sizes, they're equivalent. So it's just going to be 8, right? Because both sample size 1, N1 is 9 and N2 is 9, right? They're dependent. So calculate this. So do inverse norm, or inverse t of this 0.05, degrees of freedom 8, and put it in the wrong spot. Okay, so after inputting, I get T critical equals to negative 1.86. Okay, so it's left-tailed, so that's the only one. So now we move on to step 3. So we're going to fill in the table on the next slide. Okay, so for this part, I would go ahead and enter in 3 years ago as your list 1, and that's also x1, and for x2, that would go into list 2. So if you want to follow along, just go ahead and pause the video and input that into your list. So mine's already input. What I would do here is we're going to calculate the differences between 3 years ago and today. Of course, you can do it manually, just subtract 3 years minus today for each of them, but that takes too long. So we're going to do list. Go to the top of list 3, and then you're going to put L1 minus L2 on that list, and you should get the differences that I will go ahead and put up here. Okay, so doing what I was telling you, I did L1 minus L2 on the top of L3. You should be able to write this in. Remember, L1 is second number 1, and L2 is second number 2. So if you type that in, L3 equals L1 minus L2, you'll get this list. Now, in a similar way, we're going to find the differences squared. So we found the differences between 3 years ago and today. Now we're going to square these differences. So since we already have list 3, we could do L1 minus L2 squared, but since we already have list 3, we can just do list 3 squared. So on L4, we can write L3 squared. And that's what I'm going to do, and I'm going to write it up. Okay, so once I square the differences, I get these values. So now, as part of the formulas from the first slide of 9.3, we need the sum of the lists of the differences, and then we need the sum of the list of the differences squared. So I'm going to write it like I need this sum of the differences squared, and I also need the other sum of my differences. Okay, so we're going to get this, but again, using the calculators. If you want to just go to the home screen and then you're going to use stat right arrow to calculate 1-bar stats. And in the list, you're going to push second number 3 for list 3, and then calculate and look for the summation. And I get negative 9.73 here for that summation. And you'll do a similar thing for the sum of the sum of the differences squared. So I'm going to do it again. Stat, right arrow, calculate 1-bar stats. And this time I'm going to change it to, I want the stats for list 4. Look for the summation, the sigma, and I get 40.54. Okay, so we're going to use those for our formula that we'll need in a second. The other thing we'll need for our formula is the average difference. So how do you find the average difference? Well, the first page tells you a formula for the average difference, which is, well, basically, you know how to find an average. You sum up all the differences and divide it by the total. So add these up, divide by the total. Well, they're already added up, so we'll just divide by 9. So negative 9.73 divided by, I'm ahead of 9. Okay, it's negative 1.08. Okay, so we found what we needed for our formula, but we still need to calculate the standard deviation of our differences in order to use. I might have to squeeze it in somewhere over here. But the standard deviation of our differences formula, I'm going to write it down and then we're going to substitute it in. Okay, I had to improvise a little bit just to get it all to fit. But here's the formula from the first page of your notes. And so now we'll just input, well, we know what n is. N is 9. That's the sample size. So we're going to go ahead and plug into this formula. So here we're going to put 9. The sum of the differences squared, what is that? That's 40.54. So 40.54. 9 times 40.54 minus the sum of the differences squared. So these are not the same thing. This is the sum of the differences, which is negative 9.73, and then the square of that number. Okay, so make sure you make a distinction between these two. And n is 9 times n is 9 minus 1. See, so not too bad. Just input that into your calculator and you found your standard deviation for your differences. So I'm going to go ahead and do that. Okay, so after inputting this information into my calculator, I end up with 0.228 as my standard deviation of my differences. Okay, so after all this work, what were we trying to do again? Well, we're trying to find the test statistic. So now we have everything. We have for the test statistic, which I'm going to write up here, and we're going to calculate. Okay, so here's the formula you'll see on the first page of 9.3, or the first slide. And we'll just input what we have. So d bar, the average of the differences, we calculate it to be negative 1.08. So I'm going to input that. I'm going to do it over here. Negative 1.08 minus the mean difference. Well, the mean difference from our null hypothesis is 0, so I could just put 0 or nothing there. Over the standard deviation of the differences, which is 0.228, divided by the square root of n, which is 9. Okay, so input that into your calculator, you'll get an answer for the t-test. Okay, so I think through the screen, some of y'all were asking how I got this. Well, I got this in error on a slight misinput into my calculator. So here, let me correct this. It should actually be not 0.228. It should be Here, I'm gonna write on this side. 1.94. Okay. So apologize for that error, but that means this will change because that's the standard deviation of the differences. 1.94. Go here, and then after doing those changes, I end up with negative 1.67, which finally is our t-test, and we can place our t-test into our normal curve here, which would fall just inside the critical value of negative 1.86. So this is t-test at negative 1.67. Therefore, what's the decision? We failed to reject the null hypothesis. So that would be step 3 was all this mess. All right, step 3. And then step 4 is we fail to reject H naught, that the mean differences of deposits is 0 from 3 years ago to today. There is no differences from the deposits from 3 years ago to today. In step 5, a statement about the alternative. There is no evidence to suggest H1, that the mean differences from 3 years ago to today is less than 0. So that concludes the hypothesis testing on that question. So we'll move on to the next one. Okay, so on the next question, cholesterol levels. A dietitian wishes to see if a person's cholesterol level will change if the diet is supplemented by a certain mineral. 6 subjects were pre-tested and then they took the mineral supplement for a 6-week period. The results are shown in the table. Can it be concluded that the cholesterol level has been changed at alpha equal to 0.10? Assume the variable is approximately normally distributed. So here again you have a before and after scenario. So we want to see the differences between before and after when the diet was supplemented by some mineral, and to see if there was any changes in their cholesterol measured by milligrams per deciliter, it says. Okay, so want to see if this this mineral works, in other words, for people with high cholesterol. So we're going to go ahead and look at the numbers. We're going to state the null hypothesis, and the null, again, so step 1, the null is that the mean difference is no difference. That's usually the null. The alternative is if the mean difference in this problem, no, we got to look for the clues. So in the problem it says, can it be concluded that the cholesterol level has been changed? Changed indicating being different. So that would be our alternative that's different. So this is a what? Left-tailed, two-tailed, or right-tailed test. It's not equal to, so therefore it's a two-tailed test. And so we'll move into step 2, which will be find the critical value at alpha equal to 0.02. So the critical value for this, the same way we find the critical value in all our previous sections. In this case, critical t-value, because we have 2 samples, we're going to do the two-tailed test, because it's not equal, like we said, and since it's 0.10, our alpha over 2 is 0.05, therefore we need inverse t of area 0.05 with the degrees of freedom of n minus 1, or 6, so the degrees of freedom is 5. Input that into your calculator, we will get our t criticals. Okay, so now we're going to compute the test value, which is the fun part, like last one. So we'll write up the table or fill in the table. Okay, so to fill in this table, you would probably want to type in the before list and the after list into L1, L2, and we'll do the same thing as before, which is do an L3 list equal to L1 minus L2 to find the differences. So that's what I'm going to do and put it on the table. Okay, so doing what I described, L1 minus L2, I got this in my list 3, went ahead and copied it up here. And then L4 is you want your differences squared, or your D squared. So I'm going to do L3 squared on my calculator and then write the results on that list. Okay, so now that we have our list filled in, we want to go ahead and find the sum of the differences. And we also want to find our sum of differences squared. And we'll use the calculator for both of these. So I'll simply input, go to the home screen, and you want to input stat calculate 1 bar stats with L1. Okay, so with that said, I'm going to look for the sum of x. You know what? Actually, I take like it's stat calc 1 bar stats for L3, not for L1, because I'm trying to find the sum of this list, which the sum of that list I get to be 100. So this is 100, and we're going to do the same thing again, except for find the sum of the differences squared. So stat calc 1 bar stats for list 4 this time. Calculate, and I see 4890. 4890. That's my sum of my differences squared. The other thing we'll need is the mean of the differences. Okay, which you'll see the formula of the mean of the differences is the sum of all these divided by n, which again we know how to find an average. Just take the sum divided by the total, which there's 6. So 100 divided by 6 will give you our answer. So that's 16.67. Okay, so that's our mean difference. So now with the sum of the differences and the sum of the differences squared and the mean difference, we can go ahead and use our formula for the standard deviation, which I'm going to write over here because I'll probably need the space over there. So standard deviation of the differences, I'll write the formula and then we'll substitute. Okay, so here's the formula. Now time to substitute. So we end up with n is 6. There's 6 in the sample size times the sum of our differences squared, which we found to be 4890. 6 times 4890 minus the sum of our differences, which is 100, and then squared. 100 squared over 6, or n times 6 minus 1, all that under a square root. Input that into your calculator and you'll get an answer. Okay, so after inputting, I end up with 25.39 into the calculator. So with the standard deviation of the differences, I can now use this to calculate our t-test, which I will write up. We'll substitute. Okay, so our mean difference was 16.67 for our t-test. So we're going to input 16.67 minus our population mean difference is assumed to be 0. So we can just put minus 0 or put nothing there. Our standard deviation of our differences is 25.39. And over the square root of how many are here, 6 in our sample size. And we end up with a calculation of input into your calculator and you'll get something. So I ended up getting 1.61 as our t-test. So if I plot this onto our normal curve here, I don't believe I ever wrote the critical value. So let me go ahead and write that inverse t of 0.05, degrees of freedom of 5. I had it here, I just didn't write it. Okay, negative 2.02. So that's our T critical. Is 2.02, positive and negative, okay? 1.61, however, would fall right here, okay? Which means it's not in the critical region, therefore we fail to reject the null hypothesis, and that's going to be our step. So all this mess is step 3 again. Step 4 would be we fail to reject H naught since t-test is not in the critical region. Oh, well, let's say something about H naught. We failed to reject H naught that the mean difference is equal to 0 since, and I think we didn't put this on the previous ones, justification, since t-test is not in the critical region. Okay. Okay, so a statement about the alternative would be, since we failed to reject the null, there is no evidence to suggest H1 that the mean difference in cholesterol levels after the mineral is different, or is not 0. And that concludes our hypothesis testing for the difference between two means of this time a dependent sample. Okay, that is it for the day. I will see y'all in class next time. Okay, I was just kidding. I thought we were on the last question, but we got one more, which is the confidence interval question, but it should take no time. We're going to use the confidence interval formula for this section, which is d bar minus t alpha over 2 times sd divided by square root of n less than the mean difference, and the same thing except 4 plus on the other side, using the same values that we did from the previous problem. So let's go ahead and jump into it. So here you're going to get 16.67 minus t alpha over 2. We'll need to calculate with this one, since we have a two-tailed test. It was alpha of 0.10, so we'll do a 90% confidence interval. So we'll need to do, I'll do it over here, 90% confidence, that means 0.05 inverse t of area 0.05 with degrees of freedom. There were 6 in the sample, so 6 minus 1, that's 5. We'll calculate that on our calculators and get a t alpha over 2. So that's going to give us a the same thing that we got on the previous, which was negative 2.02, I believe. Yes, negative 2.02. So that's our T critical, or I'm sorry, my T alpha over 2, which is negative 2.02, which makes, you really want the positive, so positive 2.02. So 2.02 times the standard deviation of the differences is 25.39 over the square root of 6, less than the mean difference, less than the same thing, 16.67 plus 2.02 over the standard deviation of the differences, 25.39 over the square root of 6. Input this into your calculator and you'll get your result. Okay, so after inputting, I end up with this confidence interval, and what do I notice? Does it contain 0? Yes, it does. So this is evidence to suggest that the mean difference is equal to 0. Since 0 is, we can't go against the null hypothesis that the mean difference is not 0, according to this interval, since 0 is contained in that interval at a 90% confidence. So now that concludes the lesson for this section, and I will see you next time.